Welcome to Poker Math 101. In today's video, we're going to discuss the poker math that every player needs to know. You don't need to be a mathematician or a genius, but if you want to succeed at poker, you need to have a grasp on these basic mathematical principles that guide your strategy. Let's dive in. Before we start the video, we'd really appreciate it if you could hit the like and subscribe buttons. Your support means a lot to us. Thank you, and enjoy the video. Let's start with a question. What do these 5 things have in common? Prop bets, pot odds, minimum defense frequency, alpha, and value-to-bluff ratios. Most coaching material out there will teach you that these are 5 separate things. They all have their own equations. They all represent different concepts, blah, blah, blah. But they all share one thing in common. What is that? The answer is that they can all be expressed as a simple risk-reward calculation. In fact, to me, these aren't 5 different things. This is one thing expressed 5 different ways. In today's video, I'm going to equip you with a powerful mathematical tool that you can use to solve a wide variety of different poker math spots very easily and intuitively. We're first going to cover why this matters. We'll help you build intuition so that you're not memorizing formulas, rather you are building this from an intuitive place. Then I want to teach you the basic risk-reward calculations, how you can use those in things like expected value, edge, break-even calculations, etc. And along the way, we're going to have interactive quizzes to help drill this knowledge home. So why does this matter? I mean, at its heart, poker is a game of intuition. It's a game of guesswork, but you need something to guide your intuition, and this math guides it, right? For example, if you're calling a bet, you need to have some idea of how often your call needs to work to succeed. Even if you don't know your exact equity, you need to have some idea of, okay, it needs to work 20% of the time, or oh crap, it needs to work a lot more often than that. Math is also very useful in off-table analysis, reviewing your hand histories, reviewing your play, and building that intuition during your study time. It helps you ask the right questions. So if you don't know how to reframe this in terms of the basic mathematics that guide your strategy, then you don't know how to ask the right questions about your own strategy or how to improve. Most importantly, risk and reward weight your incentives. If you don't understand how these weightings work, then you don't understand the incentives of your play. Let's build up your intuition. You're getting 3-to-1 on a call. How often do you need to win to break even? Right now, this problem seems kind of abstract. If you're familiar with poker math, you might know the answer, but let's break this down to something a little more fundamental. Let's reframe the question in terms of concrete objects that you can understand. A gin and tonic recipe uses 3 parts tonic to 1 part gin. What percentage of the drink is gin? Hopefully, just by looking at this, you can see, oh, 1 out of 4 is gin. Therefore, 25% of this drink is gin, right? And this is just another way of saying there are 3 times as much tonic as there is gin. Therefore, 25% gin. And this is just how you transform a ratio into a percentage, right? All right, so let's go back to our previous example. You're getting 3-to-1 on a call. How often do you need to win to break even? Okay, well, we imagine 3 plus dollar signs and 1 minus dollar sign. All this means is that the reward is 3 times greater than the risk. So to break even, you need to win 1 in 4 times, or 25%. We'll try another example. You wager $100 against your friend's $400 that there will be an ace on the flop. So if there's an ace on the flop, you gain $400, but if there's no ace on the flop, you have to pay your friend $100. How often do you have to flop an ace to break even? Okay, at the moment this seems a little vague, but let's reframe it in terms of something more concrete. A basket contains 4 green apples and 1 red apple. What percentage of apples are red in this basket? Well, hopefully just by looking at this picture, you can say, well, it's 1 in 5 apples, 20%. There are 4 green apples for every 1 red apple. 1 over 1 plus 4, or 1/5, is 20%. So you can just think of it in terms of simple things like this, right? Going back to the previous question, it's your 400 against their 100. How often do you have to flop an ace? Well, you're getting 400 to 100, or 4-to-1. Therefore, you need to get an ace at least 20% of the time to break even. Now, for a quick quiz, is this a profitable bet? Will you make money or lose money doing this? Take a moment to consider your answer. Well, if we use GTO Wizard's reports, we can see that ace-high flops actually occur 21.7% of the time. So this is a profitable bet because you're going to flop an ace more than 20% of the time. Risk and reward ratios are to me, the most fundamental equation in gambling. They answer a huge number of poker math questions. Throughout this video, we'll be referencing a term called implied probability, or the break-even point. And this is just a fancy way of saying how often does the thing need to happen for the bet to be fair. In our previous example, if the ace flopped exactly 20% of the time, no one has the edge. It's exactly a fair break-even bet. And whenever you ask something like, what are the pot odds in poker? Or what's the bluffing frequency? All of these things can be expressed as just calculating the break-even point. Once you know this break-even point, you can then start to estimate whether the thing happens more or less often than that. And there's how you start building your intuition. Let's start with a breakdown. So the way we express stuff as odds is reward colon risk. You're getting 3 to 1. You're getting 5 to 1. All this means is here's the reward. It is this much bigger or smaller than the risk. It's a ratio, right? That's how you express something as odds. In order to convert this to a percentage, we use this formula. First of all, risk is what we stand to lose when we're unsuccessful. Reward is what we stand to gain when we are successful. The implied probability or break-even point is risk divided by risk plus reward, which is just how you convert the odds at the top of this page to a percentage, to the implied probability. You can also use this to calculate the expected value of something. So if you want to know exactly how much money you expect to make, well, you can just multiply what you think the win percentage will be times the reward, subtract the lose percentage times the risk. EV equals that equation right there. Again, you can understand basically all of poker math if you understand basic risk-reward calculations. Let's see an example and really drill this home. We'll start with pot odds, the most common one. And pot odds fundamentally asks, what is the risk-reward of calling? So if you're facing some bet, the risk is that you call and lose the amount you called. The reward, what you stand to gain, is the pot and their bet. If I give you this and I say, okay, you're on the river in the big blind here, button has just bet 2.7 into 5.4, so they've made a half pot bet. What are big blind's pot odds? Could you figure it out? Take a moment. All right, let's walk through it. Remember, we're trying to calculate the break-even point of calling. The risk is 2.7, so we call and lose. We stand to lose 2.7 big blinds. The reward is how much we gain if we win. So we call, we gain their bet of 2.7 big blinds and the existing pot of 5.4 big blinds for a total of 8.1. The pot odds, or the break-even point of calling, could then be expressed as risk divided by risk plus reward. Or more succinctly, this fraction, which comes out to 25%, which is exactly what you expect for a half pot bet, right? But you may have seen pot odds expressed as a ratio instead. So we know that, okay, they need to win 25% of the time. But what if I asked you this question differently? What if I said, okay, here's the reward and the risk, calculate it. Big blind is getting 3 to 1, right? Or 8.1 to 2.7. The reward is 3 times greater than the risk because you get a full pot and a half pot bet if you win, and you lose a half pot bet if you lose. So 3 to 1. Risk divided by risk plus reward. We can convert this from odds to percentages. Again, just using this equation, you need to win 25% of the time. And finally, we can express this as an expected value equation. So maybe you don't just want to figure out the break-even percentage. You want to know, hey, exactly how much money am I going to make if I win, let's say 30% of the time, 20%? Give me some exact numbers. Well, you can plug this into an EV equation pretty easily. Again, we know the risk, we know the reward, therefore we can plug it into a simple EV equation. Here's how often we win times the amount we win, subtract how often we lose times the amount we lose. Plug this in, and there you go. So you can plug in any win and lose percentage you like and figure out the exact expected value of calling. Now remember, if we set the expected value of calling to 0, then big blind will win 25% of the time. Or in other words, if we set the win percentage to 25% and the lose percentage to 75%, well, then the expected value of calling is exactly 0. Or put another way, it is a break-even call. So fundamentally, the takeaway here is that pot odds is just asking you to find the break-even win percentage when you call. That's all it is, right? So you understand pot odds, but do you understand value-to-bluff ratios? a very handy trick to know is that the bluffing percentage on the river, so how often someone should be bluffing, is just equal to the pot odds that they're laying. Similarly, the value percentage is just 1 minus this amount. Now keep in mind, this is only on the river. On flop and turn, value-to-bluff ratios kind of compound. I have a whole other video about that called Leverage. Go check that out if you want to learn how this stuff works on earlier streets. But on the river anyway, we can pretty easily express, well, hey, they ought to be bluffing this often because here's the pot odds they're laying. Let me try an example. We'll go back to the previous one. Button has bet 2.7 into 5.4, so they've made a half pot bet. How often should they be bluffing on the river? Imagine that you, in the big blind, have a bluff catcher. You beat all of their bluffs but lose to all their value bets. Well, if you're exactly breaking even, that would mean you have 25% equity, right? Because that would mean that they're bluffing 25% of the time. So you know the break-even bluffing frequency. As the big blind, you could then start to think, oh, there's no way they have 25% bluffs here, or, oh, they're definitely bluffing more than a quarter of the time here. You can start to rephrase it in terms of these key thresholds and start thinking about your strategy. Let's talk about alpha next. Alpha describes the risk-reward of bluffing. Imagine you put in some pure bluff on the river. How often does it need to work in order for you to break even? The risk of bluffing is that they'll call you, and then you just lose whatever amount you bluffed. The reward, what you stand to gain, is the pot, and this happens whenever they fold. So let's calculate the alpha of this spot here. You're in the big blind, you've just put in 6.5, so you've overbet the pot into a 5 big blind pot. How often do you need small blind to fold in order for your bluff to break even? Well, we know we're trying to calculate alpha. We know our risk is the amount we bluffed, 6.5. We know the reward, what we stand to gain, is the pot, 5 big blinds. We know how to calculate a break-even percentage. That's just risk divided by risk plus reward. Yes, it's the same formula as pot odds again. And we can just plug this in and figure out, hey, in order for our bluff to break even, we need them to fold 57% of the time. If they fold more than that, hey, we're making money. If they fold less than that, ouch, we're losing money. But how much are we making or losing exactly? Well, let's find out. We can also plug this in to an expected value equation. So the expected value of bluffing, again, we know the risk, we know the reward. It's the win percentage times the reward, subtract the lose percentage times the risk. If you want to figure out exactly how much money you're going to make and you have some estimates for win and lose percentage, well, you can plug this in. Now, in the case of bluffing, you win whenever they fold and you lose whenever they call. So I'm going to replace those terms, and then we'll plug in the reward and the risk. And from here, you can plug in whatever percentages you like. And you'll notice that if we plug in the break-even percentage, the expected value of bluffing becomes 0. But if you think they're folding more than that, well, now we're making money. If they fold less than that, well, now we're losing money. So again, if you understand risk and reward, you understand alpha, and you understand how to calculate the EV of a bluff. EV of bluff equals 0 when small blind folds 57% of the time. Let's talk about minimum defense frequency. MDF is your shield against bluffers. It's how you prevent people from running you over and exploiting you by over bluffing. So, how often do we have to call to prevent our opponent from profitably bluffing? Well, wait, isn't this what we just calculated? It is. MDF is just 1 minus alpha, and alpha is just 1 minus MDF. So going back to our previous example, if we want to calculate how often small blind should defend, or the MDF of small blind in this spot, how wide they should defend, well, okay, we already know the alpha is 57%. Therefore, MDF is 1 minus that number, or 43%. Small blind should defend at least 43% of the time. Now, they can defend through calls or raises, but all that matters is that they're folding no more than 57%, because if they fold more than 57% of the time, then big blind has a profitable bluff with any 2 cards. So knowing that key break-even point is crucial to determining whether or not you're going to have a profitable bluff, or how often you ought to defend to prevent your opponent from having a profitable bluff. And as usual, it can all be expressed as a simple risk-reward calculation. All right, so you probably think you have a handle on the basics now. Let's put that to the test. We're going to put all of these concepts you've just learned together into one example. In this spot, the pot is 5 big blinds on the river. Big blind checks, small blind bets 2.5 into that pot, and big blind makes it 12.5. I want you to find 2 things. First, how often should big blind be bluffing when they raise? And secondly, how often should small blind defend versus that raise? Take a moment to think about your answer. Pause the video if you need to. We'll start with the first question. Find big blind's bluffing frequency. So, recall that the bluffing frequency is just equal to the pot odds laid. In other words, we need to find the risk-reward of calling. On the river anyway. Again, this does not apply to earlier streets. So, what is the risk-reward of small blind's call? How often do we need to be bluffing for small blind to be exactly break even when they call a bluff catcher? Their risk of calling is the amount they're being asked to call. So they've already put in 2.5. We've raised to 12.5. So 12.5 minus 2.5 equals 10. That's the risk. We're saying, hey, small blind, would you please put in another 10 chips? The reward, if they call us successfully, is that they'll gain the pot of 5 plus their previous bet, which is now a sunk cost, like they don't get this if they fold, of 2.5 plus our raise of 12.5. So it's all of these things together, and that adds up to 20. Pot odds, again, can be expressed as a simple risk-reward calculation. 10 divided by 10 plus 20, 10 over 30, 1/3. So big blind should be bluffing 1/3 of the time because the pot odds are 33%. And if I want to find the break-even point of a bluff catcher, well, it's 33%. Step 2, we're going to find how often small blind should defend. So recall that their defending frequency is just equal to the minimum defense frequency. And MDF is just 1 minus alpha. Now, there are some formulas that calculate MDF immediately. I recommend you don't use those because they just don't work with a raise. So pro tip, always find alpha first. I want you to think about what we're actually asking here. We're saying, hey, big blind might be over bluffing. How often does small blind need to defend to prevent them from profitably doing that? So we rephrase the question, what's the risk reward of big blind's bluff? They're risking 12.5. This is what they stand to lose if they bluff unsuccessfully. And the reward is the pot plus small blind's bet of 2.5. This is what they stand to gain if they bluff successfully. Alpha, again, is just a risk-reward calculation. So risk over risk plus reward, in this case, comes out to 62.5%. In other words, big blind has a break-even bluff if small blind folds at least 62.5% of the time. So big blind's really hoping that small blind folds more often than this. Bringing that back to small blind's defending frequency, MDF is just 1 minus that number, so small blind should defend at least 37.5% of the time in order to prevent big blind from profitably bluffing. Therefore, we have our answer. Simple as that. Okay, that all sounds good and well, but here's a question. Does the solver agree with our math? Let's take a look. This is a simple cash game spot. It's checked all the way down to the river. Ace, 9, 8, 5, king. So lots of different hands get there, right? There's straights, there's flushes, there's 2 pairs, all kind of different hands, but not a lot of action so far. So we check, and because there hasn't been much action, small blind puts in a nice thin value bet, half pot, mostly representing like king X second pair type hands. Action back on us in the big blind, and you can see they're raising pretty aggressively, 16.2% of the time. But what are we representing when we check raise the river? Well, some flushes, some straights, some sets, and a whole lot of 2 pair, right? These are hands that like maybe they slowed down because the flush completed on the turn, but hey, then we didn't see any action, so now we decided to check raise the river. So we can also see that there are low pairs in here, and the low pairs represent the bluffs. And hey, wouldn't you know it, we're bluffing 32.9% of the time. That's exactly what we expect with these pot odds. Another way we can view this is to click Overview, put in the raise, and here we can see pot odds. We'll just zoom in, pot odds, 33%, right? Exactly what we expect. Another thing we can do is take a look at the Ranges tab and check out this equity distribution. Now, this long flat line here, this represents small blind's equity facing our raise. And the reason it's so flat is because most of their hands are indifferent, right? So all the hands along this line have 33% equity, give or take, facing our raise. Their equity facing our raise, and you can see that they're going to be indifferent with all of these hands here. This is the bluff catching region all the way through here. We can also examine this blue line. And so let's just take a look and see how this is divided. We can see that 1/3, so these, from here to here, this is big blind's bluffing frequency. And then this section over here, this represents 2/3. So 2/3 of this is big blind V for value, right? This is the value betting percentage. And again, it's just going to be equal to whatever pot odds are laid. So if we hover our mouse directly over this blue line and you scroll down to the bottom, this will tell you the frequency. If I line that up, you can see it says 33 at the very bottom here, which tells us that 1/3 of big blind's range are bluffs and 2/3 are value bets, which is exactly what we expect in this scenario. Finally, we can take a look at small blind's defending frequency. Now, if you recall, 62.5% of the time they're supposed to fold. So you can see that's pretty much what's happening, right? They're folding just very slightly more than this break-even frequency. And they're defending, so calls plus all the raises grouped together, about what we expect, a little more than 32.5%. Now, it's not always going to be perfectly accurate because we're turning some made hands into bluffs here, right? But you'll see that it's going to be pretty darn close in a lot of these scenarios. So we know the fold percentage, we know the defending percentage, and therefore this toy game math is going to work. So we've only really covered the basics today, and the truth is you can use risk reward for like a bunch of different things. You can use it to calculate implied odds, like how much extra money do I need to make on the river for my draw to be good. You can use it to calculate like bubble factors in tournaments. You can use it to calculate risk premiums, and you can also use it to calculate edges. I'm not going to have time to go through all of those examples, but I'll share a fun one with you that was posed to 2+2 a few weeks ago. So a colleague of mine was digging through his database and he noticed this really interesting spot. Villain bets pot on the river and he has a bluff catcher. Now he knows, according to his database, that in this particular spot, Villain seems to be over bluffing 10% of the time. By villain, I just mean the population tends to be bluffing 10% more than the pot odds would dictate. We also know that they fold to a raise 10% more than MDF. Okay. So our options are we can call or we can shove for 3 times the bet. Should you call or should you raise? All right, so I'm going to show you 2 methods. The very first method is what we'll call the hard way. And this is the way most poker coaches would approach this problem, is to first calculate the break-even percentage of, the bluffing frequency and the folding frequency, then add the extra 10% over bluff and over fold, plug that into an EV equation, and then see which is bigger. Okay, it's straightforward, it's just tedious. I'll walk you through that real quick. I'm not going to spend a lot of time on this. Here's the hard way. On the left-hand side, we have the EV of calling. We can calculate the reward, and this is the only thing I care that you understand is the risk reward. In this spot, the reward is they've put in a pot size bet. If we call correctly, we gain the pot plus their bet, 2 pots. The risk is we call and lose 1 pot. You can calculate the break-even points. You can calculate their actual bluffing frequency. You can then plug that into an expected value equation, and you can calculate the expected value of calling. This over bluffing bet is 0.3 pots. If you don't like pots, you can put in big blinds or dollars or chips or bananas or whatever other units you prefer. It's the same process. Now, EV of bluff raising, again, we're not going to go too deep into this. All I really care about is that you understand how to get the risk and reward. If you raise 3 times the bet and you're successful, well, they've put in a pot size bet, so you gain the pot plus their bet, 2 pots. If you're unsuccessful, if your bluff raise gets called, you lose 3 pots, 3 times the bet. Again, you can calculate the break-even fold percentage, add 10%, you get the actual fold percentage, plug all that into an expected value equation, and you can find that the EV of bluff raising is 0.5 pots. So Obviously, bluff raising is better than calling, right? But this was pretty tedious. This is like a lot of math. So there's another equation you can use that's actually a little bit easier. I'll show you the easy way. And this one is just EV equals edge times risk plus reward, where edge is the actual success rate minus the break-even success rate. So in our example, we know they're over bluffing and over folding by 10%. That's our edge, right? We can plug this in. EV of calling, again, we know the risk, we know the reward. We know the formula. EV call equals our 10% edge times risk plus reward, 0.3 pots. EV bluff raise, we know the reward, we know the risk. The expected value of bluff raising is just equal to our edge times the risk plus the reward. It's 10% times 5 or 0.5 pots. So we get the same answer either way. I find this formula is just a lot easier because you don't have to calculate like the break-even percentage and this and that. You can just, it's like 3 numbers. It's really quick and easy. Either way, we get that the answer is that bluff raising is more profitable than calling. But this leads to another question. Should you raise bigger or smaller than 3 times the pots? Imagine you could raise larger if you wanted to, or you could raise smaller if you're shorter stacked. What would be optimal? And again, we're assuming that they fold 10% more than MDF no matter what, and that they are bluffing more than, they're 10% more than pot odds would dictate. So take a moment to consider your answer. Do you want to go bigger or do you want to go smaller to optimize your expected value? Well, the answer is that bigger is better. And the reason is that overfolding by 10% is simply a bigger mistake than overbluffing by 10%. And the reason that's the case is because both of these can be expressed as 10% times some amount. The bet plus pot, that's our reward. The only difference is that a raise is always bigger than a call, right? So the expected value of bluff raising is going to be higher always than the expected value of calling. And therefore, even if it's a min click or an all-in, EV raise is better. The actual intuitive takeaway is that in order for this to be true, our opponent needs to be bet folding some value hands in addition to those bluffs. So this doesn't work if they never fold a value hand, right? If they're perfectly polarized, obviously your assumption that they're folding 10% more than MDF is wrong, and this just doesn't work. But the assumption is that they'll bet fold some value in addition to their bluffs, and that's where your actual edge comes from. Let's summarize what we've learned today. Once you understand risk-reward calculations, you know the fundamental math that drives poker strategy. Risk is just what you stand to lose. If you're unsuccessful, reward is what you stand to gain. Pot odds is just the risk-reward of calling, or alternatively, you can think of this as the break-even river bluffing frequency. Alpha is just the risk-reward of bluffing, which is equivalent to 1 minus MDF, and a break-even calculation can be expressed always as risk divided by risk plus reward. You can also think of this as converting odds to a percentage. We have some ratio of reward and risk, and we want to convert that over to some implied probability. Finally, we have expected value. If you know your reward, you know your risk, and you have an idea of the win and lose rates, well, you can plug that in and calculate exactly how much money you'll make or lose. And if you have an idea of your edge, that is to say, how much more successful you'll be than the break-even percentage, you can use this equation instead, which is just a little bit easier to work with. That's my presentation, guys. Hope you liked it. Hope you got something out of it. If you have any questions, hit our Discord down below. And as always, happy grinding.